Hey everyone, welcome to this explainer. I am absolutely thrilled to have all you GIS students and mapping enthusiasts joining me today. We are diving into a true masterclass on one of the most fascinating challenges in all of spatial data: how exactly we transform massive, overwhelmingly complex datasets into beautiful, perfectly readable maps. It's this incredible dance between hardcore data science and visual art, and we're going to break down exactly how it works.
Okay, so think about this for a second. It is the ultimate cartographic challenge. How do you fit a one-to-one scale world, with all its chaotic, messy reality, onto a 5-inch smartphone screen? You can't just squeeze every single tree, every minor dirt road, and every tiny building onto a zoomed-out screen. If you tried, you'd literally just get a completely illegible black smudge. There's no way. So to make maps actually useful, we have to abstract reality. And that process, which is basically the beating heart of mapmaking, is what we call generalization. All right, here's our game plan for today. We'll hit the principles of generalization, compare model versus cartographic generalization, dig into the operator toolkit, see algorithms in action, tackle multi-scale mapping, and wrap it all up with automated web services. Let's jump in.
First up, Section 1, the principles of map generalization.
So the International Cartographic Association gives us this really solid baseline to work from. They define cartographic generalization as the selection and simplified representation of detail appropriate to the scale and/or the purpose of a map. The real takeaway here is that generalization is a total balancing act. You are constantly negotiating between geographic accuracy and human legibility. It's not just making things smaller, right? It's actively modifying the details to make sure the map supplies the exact info someone needs for correct geographic reasoning without totally overwhelming them.
You know, when you zoom out on a map, say going from a view of your neighborhood out to the whole city, you literally run out of physical room on the screen. The map's actual capacity to hold information just shrinks dramatically. Because of this, when we hit that capacity limit, we have to get creative with how we abstract objects. For instance, a widely scattered cluster of 50 tiny individual houses, that has to be swapped out and replaced by a single, solid polygon that just represents a built-up settlement area. We lose the micro detail, sure, but we preserve the broader geographical truth for the viewer. Moving right along to Section 2. Model versus cartographic generalization. The absolute easiest way to wrap your head around this difference is with a quick analogy. Think of model generalization as writing the executive summary of a massive, dense report. It's mostly done behind the scenes to reduce data volume so your computer can store it efficiently, process it faster, or transfer it over a network. It is purely about data reduction. Cartographic generalization, on the other hand, is like designing the presentation slides for your audience. That happens after the data is reduced, and it's entirely focused on the visual display. It's tweaking the geometries and symbols so human eyes can easily interpret everything without getting a visual headache. It's really like a pipeline moving from physical reality to a digital product. We start with messy reality. Through object generalization, we capture a structured digital landscape, which is our primary model. From there, the path splits. We can either apply model generalization to spin out secondary compressed data models for heavy analytical GIS work, or we push that data through cartographic generalization to create the final, beautifully visualized cartographic product for the human user. All right, Section 3, operators, also known as the cartographer's toolkit. Transforming messy reality into a structured map is a rigorous process. For all the GIS students out there, this is basically your step-by-step guide. Step 1 is preparation. This is where you're adapting the scale and structuring your object classes. Step 2 is redaction, selecting the relevant features, defining your priorities, and bravely cutting out the insignificant noise. And finally, Step 3 is production, the actual graphical execution where all the visual modifications take place to ensure everything is perfectly legible. And honestly, looking at the whole workflow, it's wild how much evaluation and logical grouping has to happen before any graphical simplification even begins. You have to figure out your map's purpose, set your tech constraints, and lock in your symbol sizes way before you ever start pushing lines around. The graphics, that's just the final execution of a super strict logical framework. When we do finally get to that graphical execution, we bust out the operators. Think of operators as abstract conceptual transformations. Got a curving road with way too many vertices? Boom, that's the simplification operator. Need to combine two disconnected forest patches into one? That's amalgamation. Got a river and a road overlapping because the line thickness is just too wide at the zoom level? You use the displacement operator to nudge them apart. This is basically your fundamental vocabulary for solving visual conflicts. Section 4. Algorithms, or putting operators to work. Now, we absolutely have to keep the hierarchical relationship between these two terms straight. An operator is the abstract goal, like simplification. But the algorithm, that's the specific mathematical code actually doing the heavy lifting on your digital map. So, to pull off that simplification operator, your computer might fire up the famous Douglas-Poker algorithm, or maybe a newer one based on Visvalingam-Wyatt, which drops points based on their effective area. Simply put, the operator tells the computer what to do, the algorithm calculates exactly how to do it.
Next up, Section 5, Multi-Scale Mapping in Practice.
Here's where things get really intense. Generating maps seamlessly across different zoom levels isn't just about running a simplification algorithm on a single line and calling it a day. We run into what's called generalization complexity. The real world is full of overlapping layer dependencies. If you use an algorithm to simplify a winding river, but a city is sitting right on the shore of a specific bend, well, simplifying that river might literally leave the city polygon floating out in the middle of the water. So if you displace the river, you have to displace the city too. It is a highly holistic process, and fixing one conflict almost always creates a domino effect of 3 more. Which brings us to our final topic, Section 6, the future, automated web services. Building a fully automated, on-the-fly generalization process is basically the holy grail of web mapping, but there are massive hurdles. Historically, we just lacked formal models. Cartographic knowledge is super ambiguous. Cartographers have always relied heavily on human intuition and an eye for aesthetics. But a remote web server doesn't have human intuition. It urgently needs semantic interoperability. The machine needs to know exactly what an operator means in formal code so it can execute it correctly across a bunch of different datasets. To tackle this, modern GIS research is taking a divide-and-conquer approach. Researchers have set up very specific object-oriented models, explicitly creating separate programming interfaces for model generalization and cartographic generalization. By structurally separating the math for our executive summary data from the math for our presentation slide visuals, we can start writing much cleaner, formal rules for the computers to follow. And this is exactly why formalizing operator knowledge is so absolutely vital for the future of automated web services. Researchers are using standard data models and applying UML, enriched with OCL, which is the object constraint language. By using OCL, we are literally translating fuzzy, ambiguous human mapmaking vibes into strict, unambiguous preconditions and postconditions that a machine can execute. This semantic interoperability is the only way a remote web service can intelligently pull data, run the correct sequence of algorithms, and spit out a perfectly legible map on the fly with 0 humans in the loop. It is just such an incredible time to be studying GIS. We are actively translating the ancient, highly subjective art form of cartography into the strict mathematical language of automated machines. So, I'm going to leave you with this provocative thought. As we continue to formalize this knowledge and grant algorithms the power to creatively interpret and generalize our one-to-one scale world, what are the dynamically generated multi-scale maps of tomorrow actually going to look like? Keep pushing those boundaries of spatial data, you guys, because you might just be the ones to show us. Thanks for hanging out with me for this explainer, and I'll catch you next time.